both what are the consequences of that temperature rise. That's one component of it. And that one, I think, for scientists is a little easier to get their hands into. That like this much temperature rise, they can model that pretty well. It's going to mean these impacts on people, on food growth, on sea level rise, on animals and plants. But the hard one for temperature rise is what's the probability that we're going to get there based on how much CO2 we pump into the atmosphere. So in like a perfect world, there would be like we get CO2 to this level in the atmosphere, and that then translates to this amount of temperature rise. It's like X CO2 equals Y temperature. But like scientists just don't have a handle on that. Like how much CO2 translates to how much temperature. They've got kind of like a range on it, and that is what's called, and we talked about this briefly in one of the science reports, the climate sensitivity. You guys remember that term? So looking at slide 7 now, this is an estimate of a whole bunch of parameters scientists have tried to put on this number. How much CO2 translates to how much temperature. And so these are, all these different colored lines are all these different models that get put out there. There's Stephen Schneider's in blue. That's Ray Moody's in black. Two of our endorsers. And the baseline that they usually use for defining climate sensitivity is they use for these models a doubling of pre-industrial CO2. And how much was CO2 pre-industrial in the atmosphere? At 560 parts per million in the atmosphere, what would be, and there it is at the bottom of the graph, equilibrium climate sensitivity, when the climate system finally gets back into equilibrium with 560 parts per million CO2 in the atmosphere, how much warmer will we be? And so this is where you use these sort of probability distribution functions. You guys remember these from math classes maybe, or science classes, these PDFs. And like they don't know, right? It's somewhere, I mean, what would you guys say? What's it going to be? What's a good guess for where we're going to end up at a doubling of pre-industrial CO2?
3.
Yeah.
2 something.
Yeah,
So I mean, it's easy to, I think it's easy to get kind of caught up in some of these high peak ones here, but you got to look at all this, and it's area under each one of these curves sums to 100% probability. And there's still quite a bit of area under the
Wait, what?
4, 5,
What's
6.
the dotted ones, and why is Schneider so weird on the bottom?
Yeah.
I think they're just using different colors and dots to give the different models. And Schneider's,
It's like
Schneider's
1 to
These
4.5.
change them- I see those
so the
dates.
Schneider one, I think it says LGM, and it's not for today. I think it's using like last glacial maximum data, so I don't think it's a modern analog, whereas all these ones are, except for these two, are modern analogs. And then this is putting, I think the dots there are their median temperature. So a lot of them fall in between a little over 2 to almost 4.
So is there a difference when those have been, I mean, I'm looking at the dates where those were constructed and things changed. I mean, it looks like they're getting a little higher, but I can't really tell.
Oh, that's a good question. Now.
Like forest? Is that 2006 versus 2002?
Well, here,
Yeah.
yeah. So the dates are the dates that paper was published. Is anyone not following on the phone here? Are you guys confused? We're looking at this graph on slide 7, and Matt just asked about our more recent papers showing a higher climate sensitivity. I don't know.
Eyeballing it.
Gregory
Yeah.
is the only one that
Doesn't seem to be a
doesn't
trend.
fit.
Well, Vados is the
highest.
highest one, and his was
Yeah.
done back in 02.
Oh,
This 06 one that's pretty median.
yeah. Andronova was 01. That's low.
Yeah, I mean, it looks like they're
Yeah.
kind of converging closer to between 2.5 and 3.5. If you were to look at the, just this small sample group.
Yeah. And two of the, yeah,
Can you just be sure to repeat the question that folks asked in Oakland
yeah, sure. Was there a question? Okay, so the one, I repeated the one Matt had asked, Stuart had asked about, are they getting more sensitive more recently? And two of them, the two main things that provide the like inherent uncertainty in knowing the sensitivity of our climate system to CO2 are, well, let me ask you guys, what are some of the big uncertainties in going into coming up with this number? What makes it hard to pin down? Yeah, totally. Tipping points is one of them, actually. Very quietly spoken. And then the positive feedbacks is the other one, yeah, in the system. And when those kick in and how strongly they kick in, and positive versus some negative feedbacks, or just feedbacks in general, those are two of the big uncertainties that make this number really hard to pin down. And so generally what's kind of accepted out there is 3.5 degrees, and these are all degrees Celsius. So for a doubling of CO2 to 560, 3.5 degrees Celsius is considered mid-range climate sensitivity. So, and that one, this is something I didn't know, but in using Matt's old Professor Holmes Hummel talk that I used to help prepare for this slide came from her, that 3.5 range doesn't include feedback mechanisms. So that when you're talking about the 2 down there, that's just really, makes our climate system that in that situation we're less sensitive. And then only when you start getting out to the 4, 5, 6, 7 degree climate sensitivity, which, still has some possibility around 6 degrees there, is still an option, that we are twice as sensitive to a given amount of CO2 rise as we think, as, the best guess of 3.5. There's totally that possibility. Small, but possible. Does this make sense to you guys?
Rebecca, this is Alan.
Yeah.
Did you just say that these are not incorporating any of the positive feedbacks into the estimate?
This is the 3.5 degree estimate does not include positive feedbacks.
But the wide range of this on the right, would that include positive feedback?
Yeah.
So once you start moving up into 5, 6, 7 degrees sensitivity range, that's those possibilities exist, and that's why they're not down at the 0 probability mark there, because of those positive feedback starting to kick in. Yeah, Ben?
I know we covered this a while back, and it's like not entirely related, but what are we on track again to hit 550 by? I know this.
We'll look at that.
Okay, we're getting
Yeah.
okay.
Yep. Yeah.
So basically, if you back up a little and you were saying how, like, what's the minimum number or whatever that policymakers would look at, they would look at that 3.5 degrees.
So 3.5 degrees is the sensitivity to a doubling of CO2 to getting us to 560.
Right. So would
Right.
they see that? Like, would they incorporate that?
Well, so we haven't talked about yet. We're only defining like what the uncertainties
Okay.
are here. Yeah, and so then we're going to get into like where do we want to draw the line?
Yeah, I think the question is getting at is what's dangerous.
Right.
Right.
Yeah.
Which will
So
come
we
up.
want to come up with. So what I'm trying to get at is even if we come up with a temperature and say we want to stay below this temperature, then back translating that into CO2
Mm-hmm.
because of this range of climate sensitivities doesn't
Right.
give us a certain number. It gives us a
Got it.
range of numbers.
Got it.
Yeah. So I'm just sort of saying that there's a spectrum here, and we're somewhere in it, and scientists have a handle on it. But there's some inherent uncertainties here, basically because of tipping points and positive feedbacks, that make it really hard to get a specific number.